quartiles. In this section, you'll learn how to use fractiles to specify the position of a data within a data set. Fractiles are numbers that partition or divide an ordered data set into equal parts. Each part has the same number of data entries. For instance, the median is a fractile because it divides an ordered data set into two equal parts. Now let us move on to some basic definitions. The three quartiles, Q sub 1, Q sub 2, and Q sub 3, divide an ordered data set into four equal parts. About 1/4 of the data fall on or below the first quartile, which we denote by Q sub 1. About a half of the data fall on or below the second quartile, Q sub 2. And also remember that Q sub 2 or the second quartile is the same as the median of the data set. About 3/4 of the data set falls on or below the third quartile, which we denote by Q sub 3. Let us take a look at one example. We want to find the quartiles of the following data set. The number of nuclear power plants in the top 15 nuclear power producing countries in the world are listed below. We want to find the first, second, and the third quartiles of the data set. The data are listed below: 7, 20, 16, 6, 58, and you can see they are all over the set. First, let us write these in order. The smallest value is 6, then it jumps to 7, 8, 9, and the maximum value is 104. Please note that the median or the second quartile divide up the data into two equal parts. In this case, the second quartile or the median is 16. On the left-hand side, you can find the median of the first data set, which happens to be 9, and you call it the first quartile. The same for the second part of the data set on the right-hand side. The median of the second data set is called the third quartile. Other than quartiles, we have percentiles and other fractiles that we can talk about. In addition to using quartiles to specify a measure of position, we can also use percentiles and deciles. Here's a summary for your attention. In this table, we have the fractiles, summary of what they do, and the symbols representing them. For example, for quartiles, what they do, they divide a data set into four equal pieces, and we denote them by Q1, Q2, and Q3. The next one is deciles, which divide a data set into 10 equal parts. We denote them by D1, D2, D3, D4, and it's going to stop at D9. And finally, one of the important ones is the percentiles. Percentiles divide a data set into 100 equal parts. We denote them by P1, P2, P3, P4, and finally this stops at P99. Please note that percentiles are often used in education and health-related fields to indicate how one individual compares with others in a group. Percentiles can also be used to identify unusually high or unusually low values. For example, children's growth measurements are often expressed in percentiles. Measurements in the 95th percentile and above are usually high, while those in the 5th percentile and below, they are unusually low. Please note that for GRE and TOEFL and other type of standard exam, they use percentile as well. Let us take a look at one example. The table lists 50 Space Mountain wait time from the data Disney World wait times. These wait times are arranged in increasing order in the table. We want to find a percentile for the wait time of 45 minutes. So let us take a look at the ordered data. 10 minutes, 15 minutes, another 15 minutes, another 15 minutes. So as you can see, we have a repetition in 15 minutes. Then you have 20 minutes, 20 minutes, 20 minutes, another 20 minutes, and then you have 25 minutes, and so on. We are looking for the percentile of 45 minutes. How are we going to do that? From the sorted list of wait times in the table, we see that there are 36 wait times that are less than 45 minutes. Take a look. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, and then you have 45. So in order to calculate the percentile of 45, this is equal to 36 divided by 50, which you have 50 wait time in your collection, multiplied by 100, which is 72 percentile. A wait time of 45 minutes is in the 72nd percentile. This can be interpreted as a wait time of 45 minutes separates the lowest 72% of values from the highest 28% of values. And we write P sub 72 to be 45 minutes. Numerical data can be sorted in increasing or decreasing order. So the values of a numerical data set have a rank order. A percentile is the value at a particular rank. For example, if your score on a test is on the 95th percentile, a common interpretation is that only 5% of the scores were higher than yours. The median is the 50th percentile. It's commonly assumed that 50% of the values in a data set are above the median. But some care is basically required in giving percentiles a precise definition that works for all ranks and all lists. Consider an extreme example where all the students in a class scored 75 on a test. Then 75 is a natural candidate for the median. But it's not true that 50% of the scores are above 75. Also, 75 is an equally natural candidate for the 95th percentile or the 25th or any other percentile. In that case, ties that is equal data values can be considered when defining percentiles. You also have to be careful about exactly how far up the list to go when the relevant index isn't clear. For example, what should be the 87th percentile of a collection of 10 values? The 8th value of the sorted collection or the 9th or somewhere in between? So these are the types of questions that you're going to ask when you're dealing with percentiles. In this section, we'll give a definition that works consistently for all ranks and all lists. Let's go over one numerical example using Python. If we're given a general definition of all percentiles, we define the 80th percentile of a collection of values to be the smallest value in the collection that is at least as large as 80% of all of the values. For example, let's consider the sizes of the 5 largest continents: Africa, Antarctica, Asia, North America, and South America, rounded to the nearest million square miles. Let us create an array and call that sizes. It is 12, 8, 17, 6, 9, and 7. The 80th percentile is the smallest value that is at least as large as 80% of the elements of sizes, which is the 4/5 of the 5 elements. Take a look. Let us first sort these by sizes. So you get an array starting at 6, 7, 9, 12, and 17. Now, the 80th percentile is a value on the list, which is 12. You can see that 80% of the values are less than or equal to it. And that is the smallest value on the list for which this is true. Similarly, the 70th percentile is the smallest value in the collection that is at least as large as 70% of the element of sizes. Now, 70% of 5 elements is 3.5 elements. So the 70th percentile is the 4th element on the list, which is 12 again, the same as the 80th percentile. The percentile function takes 2 arguments, a rank between 0 and 100, and array. It returns the corresponding percentile, and it is much more accurate. So let us run the line of code. The 70th percentile from the sizes is, remember that sizes is basically an array of the sizes of the continents. The result is 12. Let us make it more interesting. From data science, import star. So from data science, we're going to import star to give us the tools that we need, like table for data handling and analysis. We're going to import NumPy as NP as usual for numerical operations. We're going to import matplotlib.pyplot as plots. Remember that 538 basically gives you the format like this. So if you're not familiar with 538 format, this is just a random example for you. Now let us begin writing some codes for the percentiles. We're going to create a list and we call that V, which includes 1, 7, 3, 9, and 5. We're going to use this list to find a specific percentile. Suppose we're using the percentile function to calculate the 20th percentile. The 20th percentile of list V is going to be just 1. So let's basically create a table and have all of these percentiles. You can see that the percent and the percentile associated to that can be written this way. The table basically creates a table with 2 columns, percent and percentile. And it basically adds rows to the table, each row specifying a percentile and a value at that percentile. For example, at 39th and 40th percentiles, the value is 3. At 41st and 50th percentile, the value is 5. What is the general definition? Let P be the number between 0 and 100. The pth percentile of a collection is the smallest value in the collection that is at least as large as P percentile of all the values. By this definition, any percentile between 0 and 100 can be computed for any collection of values, and it is always an element of the collection. So it's not going to be anything different than the values that you have in your collection. In practical terms, suppose that there are n elements in the collection. To find the pth percentile, first sort the data. We're going to find the p percent of n by dividing p by 100 and multiplying that by n. You can call it k. If k is an integer, take the kth element of the sorted collection. If k is not an integer, round it up to the next integer and take that element of the sorted collection. For example, the table sorts and sections, scores and sections contain 1 row for each student in a class of 359 students. The columns are the students' discussion section and midterm score. Let us run the code and take a look at the table. Some part of the data are as follows. In section 1, the midterm is 22. In section 2, The midterm is 12, section 2 again, midterm 23, and so on. Our goal is to visualize a histogram. What does this represent? On the horizontal line, you have the midterm, and on the vertical line, you have the percent per unit. What's the 85th percentile of the scores? We can use the percentile function, create an array, call it scores, that contains the midterm scores of these students, and then find the 85th percentile. Let us run this line of code. Create a new variable, scores. And the percentile, 85th percentile of the scores is going to be 22. So according to percentile function, the 85th percentile was 22. To check that this is consistent with our definition, we can apply the definition directly. Okay, let's begin. First, put the scores in increasing order. We're going to sort the scores, but np.sort as you remember, np.sort is a numpy function that takes an array and returns a new array with all its values sorted in ascending order. There are 359 scores in the array. So let us find 85th of 359, which is going to be 305.15. Let us do the multiplication, and this is the result. This is not an integer, so remember that. Now you're going to round this guy up. So the 306th element of the sorted array is going to be 22 again. So which is consistent with what we did in the previous slide.